Sigasi 2026.2 brings together some of the biggest improvements we've been building throughout the year, based on AI entering chip design, including modular projects recommended for new AI-assisted and future-oriented workflows, Vivado and VUnit import to stay in sync with existing toolchains, MCP extension in VS Code Copilot, and Cursor to integrate deterministic design intelligence into AI assistants and agents. An AI-ready CLI with daemon support for faster agent and CI/CD iterations. Enhanced state machine visualization. Improved dependency analysis and better compilation recipes. External compilers and compilation recipe for classic projects to move seamlessly from our legacy Eclipse product to VS Code. Modular projects let you import and remain in sync with Vivado projects. Simply create a project in the directory housing your .xpr file, then point at your Vivado installation. Once Sigasi's imported the project, all we have to do is add the Vivado libraries. This project requires UVM, so let's add it as a dependency. Finally, we also need to add Vivado's Axi UArtLite library. All Sigasi features are now active, and any change made to the .xpr project will be automatically reflected in Sigasi. Modular projects allow you to import and keep in sync with VUnit projects. Simply create a project in the folder housing the run.py file and select your Python version. All Sigasi features work immediately, no extra configuration required. Anytime the run.py changes, Sigasi will follow along. Using modular projects, you can reuse your existing build scripts. First, we create a modular project. The instructions say we should execute the compile all script. We open the generated project.sigasi project configuration file and fill in the command. Sigasi automatically finds all library mappings and all features are fully functional. Inspecting the compile all script shows it calls the multi-sim script, which calls vcom. This is how Sigasi can deduce your project configuration. The new modular projects are great for reusing IP. Let's stitch together an example. The chip we're building exists out of a GPU IP, which depends on HDMI IP. It also has some Ethernet IP, and all of them use JTAG. Finally, the test bench uses UVM. The JTAG IP is already configured as a modular project. Let's start by creating a modular project for the GPU. Next, one for the HDMI. One for the Ethernet. And one for the chip. Sigasi's now working and showing that it doesn't recognize the used IP. This makes sense. We haven't defined our dependencies yet. We add the HDMI project as a dependency in the GPU project. Then we do the same for GPU, Ethernet, and JTAG in the chip project. Note how the problem markers disappear. We're still missing UVM, which is shipped with Sigasi. Finally, Ethernet and HDMI also require JTAG. Note how easy it was to find dependencies and how easy it is to add dependencies that are already configured, such as JTAG, to multiple projects. Using the new settings format, you can import functional safety standards such as DO254. Simply open the settings.json file and include all the settings files you need. In this case, DO254 for Verilog and VHDL. Note how new diagnostics pop up in the problems view as we add the VHDL rule set. Sigasi's MCP allows AI models to source reliable, deterministic information from Sigasi. It provides the AI with project and file context lookup, diagnostics for files and projects, formatting of HDL files, and design unit symbol search. Let's give it a task. format a file, fix its diagnostics, and then list diagnostics and information about the project. Whenever you see run Sigasi _ you know the AI is making use of Sigasi's MCP. We can see that the AI makes some mistakes. We'll work on that later. As usual, the AI asks for permissions. Let's allow all for this session. With those cleared out of the way, we wait for the agent to finish working. Now that it's done, we see that it formatted the document and resolved the diagnostics. It used MCP to figure out the remaining diagnostics and the possible top levels in the design, as well as some high-level information about the project. To ensure optimal usage of the MCP server, we'll let the AI create an agents.md. Let's also ensure it avoids the mistakes it encountered at the start. As expected, the file was formatted and the diagnostic was fixed by renaming the entity. The agents.md was initialized, and a note was added to prevent the same mistakes in the future. State machine transition visualization received large improvements. Let's just show you. Comments are now rendered in green in a monospace font, as they are in your editor. Next, all conditions and their relation to one another are shown. The first transition automatically combines the two if conditions. The else-if block inverts data less than 4 and adds data less than 8. Finally, the else block inverts the data less than 8. Sigasi's dependency analysis was split up and improved. This improves its fundamental features, especially external compilers and compilation recipe generation. In this example, there is a compile dependency because of the import, a preprocessor dependency because of the macro usage, and a compilation dependency because of the instantiation generated by the adder macro. External compiler support and compilation recipe generation are now available to both classic and modular projects. Simply go to Automate Design Flow and click External Compiler. Pick your favorite external compiler and see how the VS Code task is created. Now simply add the installation path to your external compiler, and the diagnostics show up automatically in Sigasi. When any relevant files are changed, the compiler is run again in the background. Similarly, click Automate Design Flow and Automated Export, and then Export Compilation Recipe. Configure the export, and note how a JSON recipe is created that lists the compile order and required metadata. This can now feed the rest of your design flow. When any relevant files are changed, the recipe is regenerated in the background.